All right, in this video, we're going to turn our attention to actually seeing how to compute or evaluate these triple integrals. So previously, we looked at a context within which a triple integral would make sense. Like it's not just, hey, let's just make these problems longer or harder. No, there's actually many physical things that can be represented with triple integrals. But now we're going to focus on the evaluation. And what you'll see with the evaluating triple integrals is that the process, it kind of mirrors what we did for double integrals, where we first started and where our region back then was a rectangular region. Now we're going to start with our solid or our region in 3 dimensions is going to be a rectangular box, but then quickly after that we can extend it to more general regions. So let's start with the case that the region or the solid that we're integrating over is a rectangular box. And I'm just going to jump right into an example. And also, as we go through the examples, I'm not going to focus too much on the fact that we can interpret this as a finding the mass of some solid when we know its density function. I'm just going to say, here's the triple integral. Let's see how to evaluate it. So here's our first example of this process. So I'm just going to have it set up, and you'll see familiar notation. Now we have 3 integral signs, right? 3 seahorses. And usually when you're integrating over something, you put the name of that thing at the bottom. You could use R for region, S for solid. I'm going to do S. And then here's the function that we're going to integrate. A fairly simple one, 8x, y, z. And since we're integrating over something that is 3-dimensional, essentially we're integrating over a volume. So the differential now is dv. And then I have to tell you what S is. And just like how we had several ways that we can represent a 2-dimensional region, same thing. In 3 dimensions, we have a variety of ways that we can represent S. So here are just a couple of them. So suppose S is this rectangular box. Let me use the interval notation and say it's 2, 3 cross with 1, 2 cross with 0, 1, right? And in a rectangular coordinate system, the first interval given is assumed to be the interval for x. The second interval is the interval for y, and the third interval is the interval for z. So another way that this can be written in a slightly more formal way is the set of all ordered triples such that your x-coordinate is between 2 and 3, your y-coordinate is between 1 and 2, and your z-coordinate is between 0 and 1, right? So that's your set builder notation. Now, I'm not going to formally state Fubini's theorem. I'm just going to say that Fubini also works in triple integrals as long as all the limits are constant. You can set this up in any order that you like, right? In other words, you can integrate with respect to any of these 3 variables first, and then of the remaining 2, you could do any of the 2 as your second variable of integration, and then of course you'll have 1 left, and that will be your third. So let's actually figure out quickly. Let's just do a little bit of combinatorics. Combinatorics is just a fancy word for counting, right? Let's see if we can count or figure out a way all the possible ways that we could set this triple integral up, right? So let me actually do this in a different color. So how many possible ways to evaluate this triple integral? All right, well, let's think about it. We have 3 variables, and because all the limits are constants, we can start with any of the 3. So that first integral, we have 3 choices, right, to choose from, right? 3 objects that we can choose from. After we do the first integral, whichever letter we start with, well, there are going to be 2 other letters left, right? And that means we can choose any of the two. And then after we do the second integral, then only one variable will be left, and we really don't have a choice. There, our hand is forced, and we'll have this. And there's a principle from combinatorics, it's a counting technique that says if you can figure out the number of ways to complete each stage of a process, then the total number of ways that you can complete the entire process, you multiply these together. So you end up getting 6. Wow. So if you think back to double integrals in the initial case when we first used Fubini, we had only 2 ways. We could do dx dy or dy dx. Now, because we have this third variable in there, it really increases the number of possibilities, right? So in this video, sorry to disappoint you, but I'm not going to do all 6 ways, right? I'm just going to do one, actually, because the process is going to be very similar. And probably one of the most common ways, right, unless you have a reason to choose otherwise, this is how I've seen many students do this problem. They just do dx, dy, dz. So they express the differential in this order. And you can see why, x, y, z, it's alphabetic and so forth. And then now, this is where we have to attach the limits, right? And those limits are going to be based on the inequalities here. This is where we're going to attach the limits based on the order in which we're going to integrate. And the process is still the same. We're going to start with the inner integral first and then work our way out. So we're going to integrate with respect to x first. So we put the x limits on the inside integral, the inner integral, like that. And then, again, based on my choice here, dy, so that means we're going to integrate with respect to y second. So that means the y limits will go in the middle. And then we're going to have our z left, and then it's going to be, so the last pair of limits that we're going to use with respect to z are 0 and 1. And then let's bring down our function like this. All right, so that's the setup. Right? And again, if you just, block out the dz and that first integral 0 to 1, you realize, hey, we have, so if you take out everything related to z, it looks like you have a double integral. So we're just going to use the same process as before, but now 3 steps instead of 2. So again, I'm going to separate them and do them literally one at a time. So we're going to do this iterative process. So first one, we're going to go from 2 to 3, 8x, y, z, dx. So when we're integrating with respect to x, we treat all the other variables as constants. Now, because everything here is being multiplied, there are a couple of things we could do. We know we can always factor out something like an 8, but because we're integrating with respect to x, we can also factor out a y and a z. So we can take out 8yz, and then here's what we have. So 2, 3, x dx. And then we do a regular integral, and we're going to use our fundamental theorem the same way. So we will have 8yz, antiderivative of x is 1/2 x squared, limits 2 to 3. Now, anytime I see constants where if I multiply them, I get nice whole numbers, nice integers, I go ahead and multiply them. So this will give me 4yz, and then let's apply our fundamental theorem, plug in the 3 squared is 9, minus 2 squared, which is 4. So 9 minus 4 is 5. Take the 5, multiply the 4, and we get 20 yz, right? There you go. So that's the first integral down. So 1 down, 2 to go. So now we're going to take this function 20yz, and then we're going to integrate that with respect to y. Now the limits are 1 to 2. So there's next step. So 1 to 2, and then we'll have 20yz dy. So in this case, since we're integrating with respect to y, The z is treated as a constant. Since it is a constant multiple, there's an operation of multiplication here. We can factor out the 20 and the z. And I'll just go ahead and write down the antiderivative of y with respect to y. So that's 1/2 y squared. Very similar to the first integral with respect to x. It works out nicely again. We can multiply the 20 and the 1/2, get a nice whole number. So we'll have 10 and then 10z. And then now let's plug in the limits for y and apply our FTC. So 2 squared is 4, 1 squared is 1. We subtract. So that's 3 times 10z. So that is 30z. All right. And then lastly, so now let's just go back up so you can see it. So the last integral now is with respect to z, and we're integrating from 0 to 1. So last step, so 0 to 1, 30z dz. Again, pretty straightforward antiderivative. That is 15z squared from 0 to 1. And then when we evaluate now, we'll have 15 minus 0. So the answer is 15. And there you go. So that's the evaluation. And again, based on our little calculation that we did earlier, there are 5 other ways that this problem could be set up and evaluated. And it really wouldn't change much at all. Now, I want to show you something, again, similar to the triple integrals. As I said, I'm not going to redo the problem multiple ways, but I'm going to show you different ways it could be set up. Because if you remember when we were doing double integrals, there are certain double integrals that we may have used the word factorable or separable, where there's something special about the function. So let me just make a little note here. Let me set up the integral the way we just did it. So it's x, y, z, and we did dx, dy, dz, and then yeah, x goes from 2 to 3, y goes from 1 to 2, and then z goes from 0 to 1. So without actually doing the integrals, I'm going to show you that this triple integral can also be separated, because all limits, right, there are a total of 6 limits here, including upper and lower. 6 limits here. They're all constants. And this function is what we would call factorable. In fact, it's already factored for us. It's 8 times x times y times z. So the first thing that we could do is, out of the first integral, like we did up there, we took out the 8, we took out the y, we took out the z. So you can sort of put that in front of the first integral. But more importantly, that 8, because it's always going to be the same, it's an actual constant, you can actually pull that outside of the first integral, in fact, in front of all 3, I should say, right? So you just put this in the very front, and we have 0 to 1, 1 to 2, and then now I'm going to take out the yz, so we have yz there, and then what we have left is 2 to 3, and then we have our x dx, right? Now, let me just say something. We just evaluated this. We just evaluated that first integral, but I want you to notice that this is just a number now. Oh, I didn't write let me write the rest of this. In fact, yeah, let me have this. That's going to be a number. And then let me write the other differentials now, dy, dz, right? So that thing that I have in green, we haven't evaluated it, but we know that it represents a number. So just like how I was able to factor the number 8 and pull it all the way out and put it in front of the integral from 0 to 1, I can do that with everything I have boxed there in green. I can take that whole green thingamajig and put it right beside the 8, and it looks like this. So I'll have 8 times, and then the first integral is from 2 to 3 of x dx, and then times. There's going to be a times now, because think about what's left after I take what's in green, the green after. In fact, let me write it down so you'll see, because we're not going to evaluate it. We're just setting this up so you can see kind of a more efficient way to do these. So you have your dy dz. So now we have, look at how it's set up. We have a single integral here times a double integral there. But this double integral is also factorable. We can do the same thing. The second integral that we would do, or right here, is with respect to y. So the z is a constant. So I can factor the z and put it in front of the integral from 1 to 2. So I'll have 8, and then 2 to 3x dx, 0 to 1. Put the z in front there. And again, let me write something in green. What's in green now is going to be the y integral. The integral from 1 to 2 of y dy. Right? And then we still have the dz. Bring down the dz. We got to keep those differentials. But same thing, when I do the stuff that I now have in green, that's also a constant. So I can move that. In fact, I could put that wherever I want. I'm just going to choose to put it in front of the integral from 0 to 1, and then look at what we have left. So that triple integral that we started with, because of two things, because the integrand, or the function 8xyz, is factorable, and because all three pairs of limits are constant, then we can express that triple integral as the product of three single integrals. So it looks like this. So times, and then the integral from 1 to 2 y dy times the integral from 0 to 1 of z dz, right? So again, it's just really just an extension of Fubini's. And now you can see, because these three integrals are being multiplied, it doesn't matter the order of multiplication. We're still going to end up with the same number that we got earlier, which was 15, right? But the thing you want to look for is a separable, or better yet, factorable, a factorable integrand. That's our function. And we want all constant limits. Now, once you have that, then you can break down double, triple. It works for a quadruple or quintuple or n-tuple integrals. You can always just break them down to your basic single variable integrals, right? So that's how you evaluate a triple integral when you have a rectangular region. Now, so at the end here, what I want to do is actually go back and talk about this region. Oftentimes, when you start like an integral, you might look at the region first and you try to sketch it, especially in 2D, like when you have to reverse or switch the order of integration. But here I just want to go back and look at this rectangular box that we came up with. So remember, it's the 2, 3, and then 1, 2, and then 0, 1. So let's just see if we can come up with a little sketch for this thing. So I'm going to use our standard orientation for 3 space. Right, and we're going to see that this is a box. I'm just going to put some tick marks here. Let's say 1, 2, 3, 4 on each of our axes. Right, so of course that's our x, that's our y, that's our z. So x goes from 2 to 3. So right here, in fact, let me just highlight those intervals. So x goes from 2 to 3. Y goes from 1 to 2. So there. And then z goes from 0 to 1. So right there. So this is what we do. We take, so in the xy plane, you would have, I'll do it. I probably should have done those dotted, but anyway, You'll have dotted here and then dotted there, green. And then you would have dotted here, blue. So those are the Y's. And then you just go up 1 unit. So then you'd have dotted here, dotted here, dotted here, dotted here. And then you kind of connect them and you get your little box, right? So let me complete the box. So again, that's from your X. And then these are for your Y's going that direction and that direction. Yep. So that's the, I'm going to choose a different color here. So yeah, so this is our rectangular box that we've integrated over, right? And because it's a rectangle, we had lots of ways to do it. And if we interpreted our function as the function x8xyz as the density of this box, then by our computation, we found that the mass of that box was, let's say, 15 grams or something like that, right? So sometimes it's a little harder to visualize, but the nice thing is the process works the same. It's just more of the same. All right. In our next video, we're going to look at just a few simple cases where the region is not a rectangular box, and again, it's going to look very similar to what we did with those non-rectangular regions for double integrals. So look forward to seeing you then. See you soon.